Okay, so probably maybe I should cut off that and then try to continue this isotope in the second segment or something. So I have to cut up in between over here, or the first session of the lecture. Now this first lecture, I'm trying to devote whole discussion on the isotope. Isotope is, by definition, is something like same element with different number of neutrons, which means take the example of a carbon, which is easier to understand. So three most abundant in the original figure that I pick up on the internet. It reads, and the three most not abundant but original description was the most what they say is the most stable. That was the original description. But no, what do you mean by stable? That is not correct. Okay. So that's, I just took the liberty of changing that stable into abundant. Yeah, there are so many other different variety of different isotopes. First, let us just define more correctly the isotope first, and then get into the discussion of whatever the other trivials. Here, what you see is three different versions of carbon. One is labeled as a carbon 12, and you can read here 98, almost 99%, which is the most abundant version of the carbon existing on Earth, showing this 12 indicate the mass, atomic mass number. 12 means atomic mass, which means, okay, here 6 neutrons and 6 protons will make up 12 the atomic mass. Okay, that's what the regular, or maybe regular, I shouldn't say regular, but the most abundant, so to speak, C12. On the other hand, a rare version of a different version of carbon called C13. Here the number 13, which is also the indication of mass, we can infer, okay, there must be something different. Yeah, what's happening really happening over here is there is one more neutron here in the case of this C13. So having 6 protons but plus one more additional extra neutron, it makes up this C13. That's the definition of this the isotopes, which are like, they are all carbon. Yeah, they are the carbon. So they just keep the integrity of this being carbon, having particular number of protons and electrons. That's what really matters most. Especially the number of a proton is what it makes the most important in giving any particular identity to a given element. So carbon, they are all carbon, but they slightly differ in the number of protons, and then we define those groups of related element as an isotope. Okay, in the case of a carbon, like most abundant 3 varieties of isotopes, but like I said earlier, one moment ago, there are many other different versions of carbons also exist, although they are extremely rare, so there is no point of bring them up and then show to give us further confusion to our already poor brain. And here, the third type of this isotope, which is a C14, is even less than 0.1% in proportion existing on Earth. Okay. On Earth, so this is a whole average. So if you take the average and then if you examine all every different part of the earth, whether in the inside of your body or outside of in the atmosphere, probably this proportion of like 99% versus 1% versus less than 0.1% are the one that actually you are going to most of the times you are going to get the proportion of this. The existence is what it is saying. So here, two more neutrons exist on this. Okay, so that's the definition of isotopes. But in isotopes, okay, let me take care of this first. So all these isotopes are in like taking once again the example of a carbon 12, 13, 14. They are all actually identical. We can consider they are the same element, chemically speaking and also physically speaking. So they are identical in chemical and physical properties is what we can say about them. But whenever I have this thing in during the lecture, because in the regular general biology lecture, although I do not do it on the regular basis, but sometimes I do that at this university, and at least one or two students actually argue about what I say. And hey, how can you say like chemically? I don't know really about that, but how can you say it is also even physically identical, even with this different number of protons, I mean different number of neutrons? Well, yes, that is true that all these different isotopes have different number of neutrons, but still with that, overall all these their behaviors coming out from their chemical and the physical interaction and then characteristics are like negligible. The differences are extremely negligible. So we can simply assume that they are just the same material. And more importantly, for the aspect of this biology, okay, life itself does not discriminate anything among different types of isotope. Whether it is a 12 or 13 or 14, who cares? We don't know anything about it. We just, like in carbon, we don't actually consume carbon directly, or always we consume carbon indirectly through at the secondary process done by the plants. But let's take the example of a plant first. For the sake of a plant, they have to breathe in the carbon dioxide to synthesize their food, the glucose. They don't care about what kind of carbon comes in, whether it's a C12 or C13 or C14. They all will just welcome and then put them in as a component of whatever they make up. So in glucose molecule, which is made up of carbon, the proportion of C12, 13, and C14, probably if you examine, will be the identical to that proportion that exists in on Earth. This is what the point that I'm trying to make. Okay? Here is a more important part. So actually, this is the reason why I want to have this discussion opportunity about the isotope, because I want to discuss this particular isotope, which is a radioactive isotope. So among different types of isotope, two different kinds of isotope. One is so-called stable isotopes, and the other one is a radioactive isotope. In the case of carbon, the C13 is a stable isotope. If we consider this C12 as a kind of a standard or regular, then we can describe this C13 as a kind of an isotope, but it is a stable isotope, which is simply meaning that it is not radioactive. However, the C14 is a radioactive isotope. How is it different from so-called stable isotope? Is in that it has a higher energy, so it emits. It has a too much energy, so all those so-called radioactive isotope, will emit certain type of energy. Okay, three different types of energies are there. So then it will convert itself after giving off certain enough amount of energy. Then it can become a new self. So in the case of a C14, once it releases enough amount of energy, then now the C14, I am no more C14. I am now, from now on, I am nitrogen 14, which is non-radioactive anymore, and the regular nitrogen, isn't it? So that's the behavior, interesting behavior of all the radioactive isotopes. So many different elements actually have both radioactive and stable isotopes. So in the example of hydrogen, okay, so the so-called regular hydrogen having one. By the way, in the case of regular hydrogen, this hydrogen does not even have any neutron. That's strange, isn't it? So it has only one proton, and that's it. So atomic mass and the number of a proton is actually equal in the case of a hydrogen. Then that particular, the most abundant version of this hydrogen, we call that is it has a specific name of protium. It's called. Then there is isotope version, which has a one actually neutron, just like the all other elements. Then we call that hydrogen as a deuterium, which is a stable isotope. And then there goes a radioactive version of the isotope, having one more neutron here. It has this atomic mass of even 3, and the tritium is a radioactive isotope. Sometimes, more frequent than not, in these days you get to hear the name of this tritium on the news, newspaper or on other the news media, when they were dealing with this some kind of a accident or some other gossips or some concerns about the nuclear power plant. Always this tritium is being mentioned. Okay, yes, it is radioactive. Although the strength of this radioactivity in the case of tritium is very weak, just like the C14. Those C14 and tritiums, in terms of this power strength, is really very weak radioactive isotope. And here the radioactive isotope's property is that, as I mentioned, it emits the energy. Yeah, it is an energy emitting the element. And after emitting enough energy, then it can become more stable, non-hazardous, so totally new, different elements. And that process, the time it takes to become, as we call it usually, is a half-life. Actually, half of them. So it has some defined period, and during that period, certain proportion of that original radioactive isotope will emit, depending on who you are, 3 different types of energy, like alpha and beta and gamma, different types of energy, and then it will become regular element. By the way, depending on different particle, actually whether it's an alpha particle, which is an energetically speaking very weak, but beta particle and the gamma rays are very strong, and X-rays are also fairly strong too, which is also the radioactive the ray. So if you go to the clinic and then take the X-ray shot to examine your internal body, that's why you have this particular lead plate to protect, because this X-ray cannot penetrate this lead, the area lead layer. So, And on the other hand, the neutron is the strongest, but it's even the neutron cannot penetrate this concrete layer, just like that. So, point is, different energy levels of different types of radioactive energy, so are all emitted from specific different types of radioactive isotope. And speaking of this half-life, means the time it takes during which half the amount of the original radioactive material become and then decay into something else is what's defined as the half-life. So any given radioactive material, let's say if the half-life is just one period of such half-life, during that half the amount of the original radioactivity disappears here, and another half-life, that period, the half of this also will disappear. So we just keep going on and on like that until the entire radioactive materials is become changed into something else, so that now it becomes totally entirely non-radioactive. So this should be, you can understand that it should be a fairly long, tedious period during which all these things convert itself into. Okay, that's the definition of the half-life of given radioactive isotope. So, for example, in the case of hydrogen, the tritium has about 12 years of such half-life, and during which half the amount of, like if you had originally 1 gram of tritium, and within 12.3 years, 0.5 gram of this original tritium will now become helium, an isotopic version of helium, like having 3, which means perhaps one more neutrons, or one less neutron, and the helium, and still half the amount of tritium will be radioactive, is how we understand this half-life and the process of the decay. So going on with another example, like in the case of C14, look, the half-life is almost 6,000 years. So it will take almost 6,000 years to get this original C14, half of them being converted into non-radioactive nitrogen. Still, the other half remains as a radioactive within that period. It's a long time procedure. So especially in the case of the C14, it will be extremely difficult to decontaminate. If you spill over in the C14 radioactive material, because radioactive materials are a lot of times actually also being used in science research in the laboratory. I am also the one used to use a lot of different radioactive material when I was in graduate school in the United States. So like C14, dealing with the C14 and another very popular and stronger radioactive isotope like a P32 was like my favorite material. Like many of those Friday evening, I used to play with this radioactive isotope to do in my experiments. But whenever I deal with this C14, I kind of raised up my alert level to kind of almost the extreme, because I knew that if I make a little bit of a one sip of a mistake, I'm gone, because there's no way you can reverse this whole your mistake if you somehow made some kind of a little bit of contamination on your work area. Oh my, you have to wait 6,000 years until half of that your mistake has been deleted, erased, but still another half will still remain for another 6,000 years, and on and on. like this P32 I mentioned is like usually gives me a more comfort in mind, because although it is extremely strong in terms of radioactive material, but I am also strong, so I don't really worry. I don't fear any strong radioactivity. Uh, so, but in the case of P32, even if you do some kind of a stupid mistake, all it takes is just to wait for a couple of weeks, uh, or like 1 month, or and within 2 months, probably completely everything will be gone. So I don't really worry too much about this P32, the involved mishap. And there's another intermediate version of radioactive isotope, which is sulfur S35, which is a weaker but longer half-life, stuff like that. And one of the extreme example of such a long half-life is a uranium. Uranium-238 has a really complicated process of during the decay. It converts itself into many different intermediate form until eventually it decays into a particular version of lead. Okay, there are several different isotopic versions of lead, but this particular version of non-isotopic, non-radioactive lead, it will take 4 billion years. Oh my God! This is like is as old as the actual entire age of the Earth. So it's just amazing, long half-life. Why do we look at think about this isotope, radioactive isotope, in biology? Because it's been such an instrumental tool in deciphering all different aspects of biological problems in research. One such an example is in many diagnostics. That's one of the reasons why I had to play with many different types of isotope when I was in the graduate school there. So in the experiment, because the fact that radioactive isotope is useful is the energy. Why they are so useful is this. The high energy, because this strong energy emit, then it can be traced. You can specifically trace the presence of this radioactive material, then your sample where it goes into many different ways of your scientific investigation, the presence of this radioactive isotope by labeling the sample. You can trace this particular sample of your interest, right? So that's why all this radioactive material can be utilized so like heavily in many different experiments in including the medical diagnostics. And another major area of such the usage is here in this so-called radioactive dating. Okay. Another name for this radioactive dating is called radiometric dating. The same thing, radioactive dating or radiometric dating, which means like how old the sample is, it like how long ago that fossil was generated, how long ago the bone the human the person carrying this bone deceased type of tracing, estimating the time period of death. Or even in the case of a rock, it's the formation, how long time ago this particular rock was formed. Is basically you can sum up as like in the activity of a carbon or any other type of radioactive dating activity. So looking at these diagnostics first, one major area of that heavily using this radioactive material is a lot of us are already familiar with this particular technique. Is a PET scan. PET actually stands for positron emission. 글씨 좀 잘 쓰면 좋겠네. tomography. So using this particular radioactive tracer molecule is called. We can visualize some 3D types of, because this tomography means the image slicing. Computer can generate this depths of sliced images and within which you can particularly pinpoint or trace of the area or material of your interest. In this particular example, the most popular the material used as a tracer in PET scan is this FDG, which means fluorodeoxyglucose. Glucose is, you know what the glucose is, but the deoxyglucose is an analog. Analog of glucose, which is non-metabolizable. Which means if there was true real glucose inside your body, once you absorb, you take in the glucose, then it will be quickly metabolized in after broken down, and then you extract the energy. However, this glucose analog, which is in particular this deoxyglucose, which actually means the oxygen is omitted one area. It is unmetabolizable analog, so it will, even if you just take in the glucose analog or the deoxyglucose, it will stay there forever, for example, so to speak. And this fluoro version, particular fluorine, radioactively labeled the fluorine as F18. Once you just put in this, then you can follow where this fluorine labeled glucose analog is there. Your body does not know whether it is like a fake glucose, so the body cell will assume that analog is the same as the real glucose, so they actually import the glucose to try to do this metabolic process, but then it can't, so it will stay there. It is not being degraded. Eventually it will just be degraded after the decay process. That is a little bit of a complex story, but anyway, so you can use this material as where the glucose are going. Why you are particularly interested in glucose? Because in the body, glucose is regarded as a source of energy. So where particularly the metabolic activity is extremely high, all this glucose will be there. Okay? Because your body will request for the delivery of glucose to that particular area. And that is usually highly closely related with the cancer development, because where the cancer grows, they have unusually high metabolic demand, and then they will do everything in their power to attract the available glucose in your body. So together with all other glucose, this tracer acting fake glucose will be there, and then we know where that fake glucose goes, and then probably we can estimate, okay, that area perhaps might be the area of suspicions for cancer growth. And in this occasion of whatever this F18, the particular fluorine and radioactive fluorine labeled deoxyglucose, good part about this is this half-life is only 2 hours, so it will be instantly the radioactivity will disappear, which is good for your health. And the better yet, once that decays into something else, now it becomes really degradable, metabolizable glucose, which is now what's the better. So that's why it is particularly used as a very popular subject of the material tools for this PET scan. And here showing the actual real life example of this cancer development on this throat of this patient. It's got detected by this PET scan technology. And another very good example of this is actually this PET scan. I picked up the image from Wikipedia. So here all this lit area, especially the red area where you have the highly concentrated the fake glucose FDG is being detected, which is highly correlated with the suspicious cancer developing area, except for this area of the bladder. Where are your bladder? The bladder area, which is here. It doesn't count because it's a waste, the breakdown product. But mostly, what your attention should go is this area where you can find a lot of this radioactivity is being picked up in the liver. And the the description goes like this: the masked tumor developing, the tumor is actually the one originated from colon cancer. Is now this patient is undergoing, so to speak, the metastatic tumor developing stage, and all those detailed medical information at this point, who cares about? We don't have to worry about anything. But the only important point that we can take out of this is, yeah, this is an example of using the radioactive isotope to have a tracing tool in all different areas of medical diagnostics. Well, yes. And this carbon dating and other similar radioactive isotope using the dating procedure, which is also called radiometric dating, is another very important area of using the isotope in the biological research. The radioactive dating is also called radiometric dating, the same thing. Utilizing the half-life of particular isotope, we can estimate precisely, very accurately, how long ago this person or animal once lived, the object have deceased, or in the case of non-living material, how long ago it was originally formed. The type of information can be obtained. So in radioactive dating, the half-life of a particular radioactive nuclei, radioactive isotope, what I mean, is examined. So with respect to the particular half-life and how much proportion of this radioisotope remained in the body of this dead sample or non-living samples, to estimate the date of death or date of formation. For example, using the carbon C14 dating, if you found bones belonging to a mysterious person, it could be the ancient Neanderthals or some more recent individual. The way you can determine which one was that is like the principle. In principle, while the person was alive, whether the person was a Neanderthal or some medieval individual, during those lifetime, all this material exchange must have been maintained. So the portion of C14 remained inside of the body will be equal to that of the outside. And we already know the how much portion that you can expect. Like in the case of C14, it will you expect to find that less than 1%, 0.1% actually. But once the person is dead, ever since, then that material exchange is blocked. So without having any kind of a replenishment from the external source, the remainder of C14 inside of the dead person will start decaying. Okay? That you can estimate how long ago it actually started decaying, because you know the procedure, and any those material who went through this decay will be something that is which is like different from what is expected in terms of these proportions. That's the idea, principle of estimating the time after the death. So what's going on? Why it's not moving? Move up, damn it. So up to about 60,000 years, this C14 dating can be accurately estimated using. But not all those samples were dead or alive, non-living or once lived, have only like the lifespan of 60,000 years. So those material having the history of much longer than 60,000 years, you can depend on something else, like how about this uranium-238, which is once again you are doing this, forget it. So forget it, I'm not going to use this guy. So this uranium dating can be utilized like for the samples, in particular like those very old sample, like because it can generate a very accurate estimate of like the one with even 1 million years ago, ranging from 1 million years to 4 billion years of those samples. So even if that's just a 4 billion years ago sample, like it's just almost as old as the Earth's historic age. So no problem for the uranium anyway. So that is the basic principle that you're going to use. Okay. So having said that, I don't like you. This totally I'm going to do just without you. Then how about this? For example, if this carbon dating be applied to a living object to estimate its age, like how about me? Like can you estimate my age? Because I might be lying. So if I said I'm a 60 years old, or can you believe it? Or I'm a 25 years old, can you believe it just by looking at? Or is there any more accurate way of let's use it the radioactive dating to find out that guy's real age? No, you can't, because in this case, this radioactive dating cannot be applied to a living person, just because of the reason I have just explained. So the live object, whether it's an animal or plant or anything, they will have a constant exchange of the material between inside and outside. So the you cannot have anything like something like decaying procedure, and so based upon that decay, you like compare this half-life, and during that half-life, the amount of actually the isotope that decayed into, because you will have just constant exchange of those material. So the amount what you have in those radioactive isotope inside of your body will be equal to, in terms of this proportion, to that of the outside of the world. However, once you are dead, then it's totally different story. In that, everything will be blocked, and then inside you start showing of your own niche and egos, and then start decaying procedure. So after a long period of your death, so death has to be the first premise. You have to die in order for being a subject of this estimation, the radioactive dating process. Then you can see how much of the C14 or anything like any radioactive isotope that you have still inside is actually something that agree to what is expected in the outside, and then that the difference would be the time. Okay, the time that has elapsed after your death. Okay, so it doesn't matter, no matter how short the half-life of the radioactive material you used, there is no way you can apply that principle to the living object. Okay, so with that, I can finish all those discussions about the first part of the whole this chapter 2. Actually, the first part was the lightest things, but already I have noticed that I have spent way too much time on this. So that should be a shame, and I will have to probably split this segment even two, lecture 1A and 1B, something like that, to have a lesser length of each lecture period, like I said. Having said that, let's see. See you in the following section of the lecture after finish the editing of the first lecture. Okay.